This is the continuation of chapter 4 chemical bonds, part 2. So I talked about the chemical bonds and I talked about single bonds, double bonds and triple bonds and how the covalent molecule share these electrons. And now moving to a new concept which is called electronegativity. So electronegativity is a measure of an atom's attraction for an electron in a bond. So here's a periodic table, and if I have to depict electronegativity in simple terms, I will show you like this. So it increases in this direction, so from left to right, and then it decreases from top to bottom. So noble gases are not included. So here in that case, if it's increasing in the period 2, if we look at period 2, then see fluorine has an electronegativity of 4. So numbers here are telling you the electronegativity for that element. So 2.1 for hydrogen, fluorine has 4, chlorine has 3, bromine. You don't have to memorize these, but it's important to know this trend that it increases from left to right and it decreases from top to bottom. So if I ask you from all the elements listed here, which one is most electronegative element, then you should be able to point out that it is fluorine, even without seeing these numbers, because you know the trend of it's going on increasing from left to right and it goes on decreasing from top to bottom. So that leaves fluorine as one of the most electronegative elements. And why am I talking about electronegativity? Because I'm going to switch to something called as polarity, and we need to understand the concept of electronegativity. So what are polar covalent bonds? We already know the covalent bonds where the electrons are shared. So in polar covalent bonds, let's take an example of hydrogen chloride here, and from the table that I showed you, or from the chart that I showed you in the earlier figure, you saw that hydrogen had electronegativity of about 2.1 and then it increased from left to right. So chlorine here chlorine was sitting right below fluorine, so it has electronegativity of about 3. So you know there is, from those numbers you can say that, oh, there is a huge difference in the electronegativity. And as we define that term, we learned that it's the ability to attract electrons in a molecule. So in for these two elements in hydrogen chloride bond, chlorine has more ability to pull the electrons towards itself, right? So you can think of it like it's pulling all the electrons towards itself. So the bonding electrons are drawn closer to the atom with the high electronegativity. And such a bond where you can see a separation of the charges is referred to as a polar covalent bond. So these delta positive and delta negative are the small or the partial charges on hydrogen. So delta positive is hydrogen, delta negative is a charge on chlorine, and polarity is sometimes or is shown generally with an arrow and a cross like this. So wherever the arrow is pointing, that means the bond is polar, and it is polar or polar towards chlorine, or the more electronegative element. So that's what is shown in part B here, figure B. This is actually a electron model or electrostatic potential diagram, where you see this unequal distribution of electrons. So chlorine has more electron density than hydrogen, and that's why chlorine is delta negative and hydrogen is delta positive. And this color, blue versus red, is also telling you the same information, is also giving you the same information. So moving on, so bond polarity is then represented on a Lewis structure. So hydrogen, chlorine. One more thing that I should point out here is, so you know, for Lewis structure, you know, hydrogen has 1 electron, and then you know chlorine has 7 valence electrons. So 1, 2, 3, 4, and then 5, 6, and 7. And then these hydrogen need 1 more electron to form its duet, and chlorine needs 1 electron to form its octet. And that's how they share these bonds to form this single bond. And these electrons which participate in the formation of this single bond are called bonding electrons, and the remaining electrons are chlorine are called the lone pair electrons, which do not participate in bonding. Anyways, that's I wanted to explain that term to you. So in bond polarity, you can represent by drawing the Lewis structure, either by showing these partial delta positive or delta negative charges, or as I told you before, you can show it with the arrow. Arrow like this, pointing towards the more electronegative atom. So that means the bond is polar. And there is another way where you can use this electronegativity difference, and then you can predict the type of bonding that a molecule has. So the difference in electronegativity between these two bonded atoms tells you what type of a bond it is, and the general rule of thumb is shown here. If the difference is less than 0.5, the bonding is non-polar covalent. If the difference is between 0.5 and 2, we call that bond polar covalent. And if it's greater than 2, then the bonds are ionic. So let me give you an example. So let's consider an example of hydrogen. You know, hydrogen each has 1 electron. So they form this single bond, right? And if you know it's the same atom, so the electronegativity will be the same. So the change in electronegativity, or the electronegativity difference here, is 0. So it's less than 0.5. So the bond is non-polar covalent bond. Covalent is understood here, non-polar covalent bond. Now let's take an example of, we saw that HCl is a polar bond, so let's just take an example of HBr, hydrogen bromide. So it will also form a single bond, and hydrogen was, the electronegativity of hydrogen was about 2.1, and bromine, if you'll have to refer to the table here, and if I ask you a problem based on this concept, you need to know what this table means, but the electronegativity values will be given to you. For example, if I ask you for HBr, then I will give you the electronegativity of hydrogen is 2.1 and bromine is 2.8. So all you have to do is 2.8 minus 2.1, which will be equal to 0.7, and 0.7 is falling between 0.5 and 2, so you know it's a polar covalent bond. And let's take an example of an ionic molecule. So let's take magnesium oxide. Okay, so you know MgO, right? You know its form of magnesium ion and oxide ion, O2 minus Mg2 plus. And if we look at the table for the electronegativity values, then magnesium's value is 1.2 electronegative value, and oxide is, or oxygen is 3.5. So 3.5 minus 1.2 equals 2.3, and that is definitely greater than 2, so we know that it's ionic. But you could also, if you know these ions, then you already know it's ionic bond. But I just wanted to demonstrate to you an example of how you can predict if the molecule is bonding, non-bonding, or ionic when you know their electronegativity values. Okay, so now we come to something called as a polyatomic ions, and as the name suggests, polyatomic, that means more than one atom, multiple atoms. So they are the groups of covalently bonded atoms, and because the name says ions, so you know that they will have a charge to itself. So think of it as different atoms are sealed together and they have a charge. So they are different atoms, but they function together. So they are a group of bonded atoms with a charge. And here are some of the examples. Only two of them have a charge of +1. Other than that, all polyatomic ions are negatively charged. So ammonium ion is NH4 plus, hydronium ion is H3O plus. So this is one more thing that you'll have to memorize, one more table that you should know. So you should know the charges, the names, and the formulas. So then let's see, hydrogen carbonate has a charge of -1, hydrogen, and then CO3 is a carbonate. Or hydrogen sulfate is HSO4 minus. Like that you have acetate ion. Some of the most common ones are these nitrite, nitrate. Whenever you have this ITE and ATE, that means there is a difference of one oxygen atom. So nitrite or ITE usually has one oxygen less than ATE, which has one oxygen more. Cyanide ion, Cn minus, hydroxide ion, OH minus, diphosphorus phosphate ion, H2PO4, permanganate, and then you have these with the -2 charges, which are carbonate, sulfate, chromate, and hydrogen phosphate ion, oxalate, and dichromate. And then the one with the 3- charge is the phosphate ion. So PO4, 3-. So it's important how you write these. So the minimum is know these ions with respect to the exam point of view. So now how would you write formulas using these polyatomic ions? So whenever you're writing these formulas which contains these polyatomic ions, you make use of parentheses, okay? And you usually put your polyatomic ion inside this. So that's telling you that it's 1 unit. And if you have more than 1 atom, then you will put a number in the subscript to tell how many atoms or how many polyatomic ions are present there. So let's look at an example. So here is the name of the compound, which is calcium nitrate. So just by looking at this name, you know calcium. So the symbol for calcium is Ca, and it's a cation, and it's in group 2, so it's 2 plus. Nitrate is NO3. It's a polyatomic ion, NO3, and it has a charge of -1. So you don't have to write -1. Minus itself represents that there is 1. If it is more than 1 charge, then you can write it down. So now I have to write, I know the parts of the name, but now I have to write the formula, right? So for calcium, there is 1 nitrate, right? But there are, look at the charges. The charge here is 2 plus, and here the charge is only 1. So we always want to write the formulas which are neutral in charge. So what does that tell you? To get to a charge of neutral, you need to have 2 nitrate ions. So then in that case, the charges will be 2 plus 2 times -1, and that will make it a charge of 0. And I will write my formula as Ca. I'll put the polyatomic ion. Nitrate, remember, is one thing. That is why NO3 is one entity, nitrate. And that's why it's in the parenthesis. And then I just showed you that there are 2 nitrates. So that's why I put the 2 at the bottom. You can also use something called as a crisscross method, which is, you know, the charge on calcium is 2. You know the charge on nitrate is 1. And then you crisscross these. So then the formula will be calcium, 1 calcium, NO3 in the bracket, and the 2 goes to nitrate. And if you do the math, then again it will be a neutral like this. So use any one of these methods to write the formulas for polyatomic ions. Okay, so when you're naming a polyatomic ion where now ammonium ion as well as sulfate both are polyatomics, right? So you will use you will simply name the ions in the order. So A comes first and it's a cation, so you said ammonium, and SO4 is sulfate, so you'll say ammonium sulfate. And see how again the charge on sulfate was what? So ammonium ion NH4 plus, right? It was +1 charge. And if you refer to the table, sulfate is SO4, 2 minus. So if I go with my crisscross method, ammonium is 1, sulfate is 2, and I crisscross the charges, then my formula will have ammonium, put the parenthesis, 2 belongs to now ammonium, and then I'll just write SO4 because there is only one SO4. And if you do the math, then you see 2 times +1 plus 2 minus will be 0. So that will be neutral. So ammonium sulfate. So if the formula is given, this is how you'll write the names. If the name is given, this is how you will write the formula. So I showed you both the methods. Okay, so now we are going to move towards the rules of how to write down these Lewis structures. So in your class, you're expected to write down simple Lewis structures. In your case, the formulas will be given because it's a multiple choice exam, so you can pick the correct one, but in order to pick the correct one you need to know how to write them, right? So here are the rules. We begin with counting the valence electrons, then we sketch a skeletal structure. We place the electrons as lone pair around the outer atoms to fulfill the octets, and subtract the electrons used from the total number of valence electrons, and then whatever is remaining electrons you put it around the central atom. So if central atom does not have an octet, you move one or more lone pair of electrons from the outer atoms, and you can form a double bond or a triple bond to complete the octet. Okay, so these were just the rules. Now I'll show you. Oh, before example, I want to show you this table 4.6, which is basically telling you the number of bonds formed by selected elements. So here, first one is hydrogen, and they've shown the Lewis symbol of hydrogen with the one electron here represented as a dot. Now, whenever it's at this point, I think it's good to introduce you to the HONC, HONC, HONC rule. That's a shortcut that you can remember. What it tells you is hydrogen will always form one bond. Okay, oxygen will form two bonds. Nitrogen will form 3 bonds, and carbon will form 4 bonds. So if we have to look at an example, let's see. The first example is HCl, and see how many bonds did hydrogen form? 1 bond. Now if we want to look at oxygen, let's look at the molecule of water. So H O H. So oxygen forms these 2 bonds. For nitrogen, let's look at ammonia, NH3. So nitrogen here is forming 1, 2, 3. Or in the case of dinitrogen, which is N2 gas, all it does is forms triple bonds. 1, 2, 3, N. And carbon, as I said, forms 4 bonds, and that can be seen here in carbon tetrachloride, or a simple example is methane, which is CH4. So carbon is the central atom, and you have 1, 2, 3, 4. So there are 4 hydrogens at the terminal end. Telling you like how carbon forms 4 bonds, or in this example as well, see 3 hydrogens represented by these gray dots and chlorine represented by the green dots. And if you're wondering how am I getting that, then it's the Lewis structures. Okay, so Lewis structure, first thing is you draw the dots, then you bring in the other element, and this HONC rule just helps you to predict the number of bonds that can be formed with these common nonmetals, hydrogen, oxygen, nitrogen, and carbon. So it's a way to check. So here you are able to see the number of bonds that can be formed and I already gave you a shortcut for that, which covers already hydrogen, carbon, nitrogen and oxygen, and then you can look at the others. And here is the representative molecule, how these molecules will be drawn on a piece of paper, and then this ball and stick model kind of gives you a three-dimensional view to see the same molecules in the spatial arrangement, but in 3D. Okay. So now let's practice writing some Lewis formulas. First, the molecule here is methanol, which is CH3OH. The first thing was count the total number of valence electrons. So carbon is in group 4A, so you know it has 4 valence electrons. Next is how many hydrogens do you have? 3 plus 1, 4 hydrogens. So you do 4 times 1 because 1 is the valence electron for hydrogen. And then you have oxygen, which is in group 6A, so it has 6 electrons, 6 valence electrons. So when you add them up, you get a total of 14. Now the second rule was we start doing a skeletal structure, and the least electronegatives will be on the corner, terminal ends. So let's draw the structure. So carbon and oxygen are bonded to each other because they're more electronegative than hydrogen, and all the hydrogens come on the all the hydrogens are on the terminal ends. So this is by skeletal structure then. Now let's look at the bonds. So what did we learn? Carbon has 4 bonds, right? So 1, 2, 3 and 4. So 4 bonds, and we learned in the earlier section that 2 electrons make a bond, right? So how many electrons are used up in these 4 bonds? Oh, excuse me, there is one more bond here. 5th bond is between oxygen and hydrogen because oxygen forms 2 bonds, right? So here's one bond of oxygen and the second bond of oxygen, and the other are 4 bonds of carbon. So 5 times 2 is 10 electrons, so we will subtract this 10 out of 14, and we are left with now 4 valence electrons. So now you will place these 4 valence electrons as lone pair on oxygen, because let's count if they have completed, if the other molecules have completed the octets. So hydrogens, remember, they need only do it. So 1 electron, 2 electron, hydrogen is good on all the sides. Then look at carbon, it needs the octet. So let's count 1, 2, 3, 4, 5, 6, 7, 8. So carbon has 4 bonds. Each bond contribute to 2 electrons. So 4 times 2, 8. So carbon is good. This terminal hydrogen here is also good. So what happens to the oxygen? Let's count the bonds first. 1, 2. 2 bonds. 2 times 2. So 4 electrons. And it needs 4 more to complete its octet, and that's why we put these lone pairs on the top and the bottom. So now it's a stable structure, and every carbon and oxygen have octets. If you have to look at how to write the Lewis structure for an ion, in this case it is tetrafluorobromate ion. So let's look at this one. So first is count the valence electrons. Now if you remember, because it's an anion and it has a negative charge, that means it has 1 electron more. Now instead of negative charge, if there is a positive charge, then you will subtract that extra electron. Okay, so here in this case you have 3 from bromine, 4 molecules of fluorine or 4 atoms of fluorine times 7, because that's the valence electrons for fluorine, plus 1 for the charge. So you have 32 electrons, 32 valence electrons, and then you start drawing the skeletal structure. So you have bromine at the center and fluorines at the terminal ends because they're more electronegative than bromine. Sorry, I'm saying bromine. It is boron. It's not bromine. So it is actually so here is a Lewis, how would you write a Lewis formula for boron tetrafluoride ion? So bromine, sorry, not bromine, boron has 3 valence electrons, fluorine has 7 valence electron, and there are 4 fluorines, so 4 times 7, and plus 1 is because of this negative charge here. So you have 32 valence electrons here. So you'll start with the skeletal structure. Your boron B will come at the center and 4 fluoride ions are on the outside. And in the beginning you will show these electrons here on all fluorine, and then there is 1 here and 1 for boron, and that's how you form this bond. But anyways, so this 4 times 2, because of these bonds, the 8 electrons are used up. So 32 minus 8 will give you 24. And what is it telling you? It's telling you that you can have up to 6 electrons. So if you draw these electrons for fluorine, you can get a octet. So let's count. So B has 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6, 7, 8. It has a complete octet. All the fluorines, they have 1, 2, 3, 4, 5, 6. And there are 4 of them. So that's why 6 times 4, 24. And the 7th electron is already used up here. And then remember, it has that 1 extra electron that was used up here, and you still have the negative sign shown here. So we have assigned the 32 electrons, and everything has completed their octet. So it's a good structure. And that extra electron that we had used, if we put this bracket and show the negative sign here, it accounts for that. Here's one more example of carbon dioxide. So carbon, you know, has a valence electrons of 4. Oxygen is 6. So 2 times 6 is 12. 12 plus 4 is 16. More electronegative elements are oxygen. So they are on the terminal ends. Carbon is in the center. And then you start assigning the electrons, right? So you know that carbon is in the center, so you put these two skeletal structure, you join them with the bond, and let's count. So 1, 2, 3, 4. We know carbon is not full, but we first make sure that outer electrons have the complete octet. So basically carbon, oxygen, oxygen, and then let's start drawing the electrons. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, and the bond 7, 8. So now we have assigned all the 16 electrons and nothing remains. But what's the problem here? The carbon does not have an octet. So what we do is we can bring the lone pair of electrons here, the lone pair of electrons here, and then we can show it as a double bond, oxygen, and then remaining electrons 1, 2, 3, 4, and here 1, 2, 3, 4. So as long as they have the octets, it does not matter if you are showing it here or here. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So now the carbon has an octet, this oxygen has an octet, and this oxygen has an octet. So it's a structure. Remember that some molecules have odd number of electrons and they are referred to as the free radicals. So whenever there is an unpaired electron left, it's referred to as a free radical. Example here is nitric oxide. It will have nitrogen plus oxygen, so it will have 11 electrons. Nitrogen dioxide will have 2 of oxygens and 1 of nitrogen, so 17. And then chlorine dioxide will have 7 from chlorine and 12 from 2 atoms of oxygen, 2 times 6, so that will be 19. So when you draw, you see they're odd pairs, right? 11, 17, and 19 electrons. So there will be one unpaired electron in all these free radicals. And remember, they're highly reactive and they exist only for a small fraction of time before they react with another species to form something else. So it's important to know what a free radical is. So odd electron molecule, or the molecule or an atom which has unpaired electrons, are called free radicals. Know the examples as well. The last part that we are going to cover today in this chapter is a theory called as VSEPR theory, or valence shell electron pair repulsion theory. And this theory is used to predict the shapes of the simple molecules from the Lewis formula. So we already learned the Lewis formulas, how to go one step further to answer the questions about the molecular shapes. So what this theory does is it predicts the shapes of the molecules and polyatomic ions based on the repulsion of the electron pairs on the central atom. So the two important terms in here, one is called as the electron set. Whenever we talk about electron set, we will refer to the lone pair on the central atom or a bond between the central atom and other atoms. So that bond can be single, double, or triple. We will still count that as one. These electron sets, then they arrange themselves in such a way that they minimize the repulsion between the like charged particles. So for example, there are two molecules present, so they will repel each other, so they'll go farther away from each other, and the farther away they are, it will affect the geometry of the molecule or the shape of the molecule. So let's look at this slide, which tells you about how these arrangements are determined. So determination of the arrangement of electron sets in a molecule based on this maximum separation and minimum repulsion. So valence shell electron pair repulsion theory. VSEPR. Okay, so if there are two electron sets, you can have a circle, and the two possible angles that you can have is alpha and beta, and they will make it up for 360 degrees, right? Everyone knows that the circle has a 360 degree angle, and for the optimal angles for the molecules or for the electron sets to be further away or they're separated maximum, the best shape that you can have or the optimal angle that you can have is this 180 degree, right? And when you have this 180 degrees, the shape of the molecule is referred to as linear. Okay, so this is one central atom. These are two other atoms, and then they're separated by 180 degrees. Linear shape. The next is when you have three electron sets. So for three electron sets, then you have to divide this into three angles, right? So the optimal angles in that range is 120 degrees. And whenever you make a shape, then it is called as a trigonal planar, and this is how it looks like. So central atoms, all these are separated from each other at an angle of 120 degrees, and the shape is referred to as trigonal planar. When you have four electron sets, what do we do? So here they're trying to show in 3D all the angles, and the bond angle is then 109.5, and the shape of the molecule is called as tetrahedral shape. So here's the central atom, here are the three, and this is the fourth atom attached to it, and this angle between the bonds is 109.5, then the shape is tetrahedral. So we have the bond angle for linear, what is the bond angle for trigonal planar, and what is the bond angle for tetrahedral. So then your book gives you this table where the molecules that you need to know in this class are listed. So it tells you the number of bonded atoms, number of lone pairs, number of electron sets. Remember, we defined the electron sets in 2 slides back. And then what is the molecular shape that is depicted, and these are some of the examples of the molecules. And here are again the ball and stick model to give you a better view of molecules and also to get a 3D dimension of it. Okay, so whenever you have two bonded atoms, okay, and there are no lone pair of electrons, so because you have two bonded atoms, the two bonds are then referred to as the electron sets. So you have two electron sets, and this is the simplest shape. It's a linear shape, right? And the example is beryllium chloride, mercury chloride, carbon dioxide, or HCN, where you have a central atom and two atoms separated by 180 degree angles in a linear shape. That's one of the easiest one. Then when there are three bonded atoms, so I'm going to change the color here. So you have three bonded atoms, no lone pair of electrons. So remember, lone pairs are the ones which do not form the bonds, they just sit on an atom. So because there are no lone pairs, these bonded atoms become the electron set, and now you have three, and we just saw that the shape in that case is called as trigonal planar. The angle here is 180. The angle for trigonal planar is 120. And the molecules are like boron trifluoride, aluminum tribromide, Here's one organic molecule. So you have a central atom. The rest of the molecules are separated by a bond angle of 120 degrees. Then when you have 4 and 0 lone pair, the electron sets are 4, it's tetrahedral. And now the examples are methane or carbon tetrabromide or silicon tetrachloride, and this is how the tetrahedral will look like, and the bond angle will be 109.5. Okay, so these three we also saw in the earlier page. Things start changing when these lone pairs start appearing. Okay, so when you have, I'm going to go in the reverse order now. So when you have 2 bonded atoms and 1 lone pair of electron, okay, so when there was no lone pair, it would have been linear, but now this inclusion of 1 lone pair leads to the 3 electron sets, and in that case our shape becomes a bent. Okay, it's called bent shape. So for example, sulfur dioxide or O3 ozone, they have this bent shape. When you again have 2 bonded atoms, but they also have 2 lone pair of electrons, then the electron sets will be 4, and the molecular shape is referred to as a bent, and that is the case on water or hydrogen sulfide or sulfur dichloride. So in that case, here is water. So if I have to show you, water is like this. So it has 2 bonds, and it also has 2 lone pair of electrons. And because of that lone pair electrons, we so if you just counted these lone pair of electrons, we know there are 4 electron sets, right? And whenever we have 4 electron sets, the geometry should be tetrahedral. But in this case, because we have 2 lone pair of electrons, we do not get the tetrahedral. We have a bent geometry. And when you have 3 bonded atoms and 1 lone pair of electrons, okay, so then again 3 plus 1 becomes 4, and ideally speaking that could have been tetrahedral, but because we have that 1 lone pair, what happens is we still have this base. So you have nitrogen, for example, if it is ammonia, so it has nitrogen and hydrogen, nitrogen and hydrogen and hydrogen, and this lone pair of electrons sits there, and that is referred to as, that geometry is referred to as trigonal pyramidal. Okay, and classic example is ammonia or phosphorus trichloride. So you have to the first 3 are very logical, and then you can think of it as, okay, I have 3 bonded atoms, and when I have 1 lone pair, then instead of getting a tetrahedral geometry, this lone pair takes up that space, and I end up getting trigonal pyramidal geometry. When I have 2 bonded atoms and 2 lone pairs, these lone pairs sort of take up this space, and there is a change in the shape, or the shape because of these repulsions is then the bent shape. And the last one was when you have 2 bonded atoms and 1 lone pair, and the number of electron sets are 3. Instead of getting this trigonal planar, the lone pair kind of sits here, So that's why you get only the bent shape. So here are some of the same rules which determine the shape of the molecule. So first step is always Lewis structure. Then you are going to count the number of electron sets. That's the whole thing about VSEPR around the central atom. And then you will follow the steps and refer to this table to predict the shape of the molecule. Now in the exam you will not be given this table, so you'll have to again depend on your memory. So if there are no lone pairs, you know whatever is the shape from the step 3 will be the shape of the molecules. If there are lone pairs present, like how I explained you in the earlier slide, then the shape of the molecule will be different depending on if it is one lone pair or two lone pairs. So that's how you will predict the molecules or shape of the molecules. So let's look at this example, the first example here for H2CO molecule. And here is the Lewis structure of the molecule. So carbon in the center, oxygen on the end, and hydrogen on top and the bottom of carbon. So let's count the number of sets. So this carbon is my central atom. So one bond here is one set, second set, and the double bond will count as 1, 2. So 1, 2, 3. So there will be 3 sets of electrons. Now, what did we learn about the 3 sets? Whenever there are 3 sets of electrons, the geometry or the shape is trigonal planar. So we will put these molecules or these hydrogens in a trigonal shape, and remember the bond angle is 120 degrees. So here is how the shape will look like. The second molecule is SCl2, and here is sulfur, 2 chlorine atom, draw the Lewis structure. So this is how the Lewis structure will look like. And let's count the number of electron sets. So this sulfur is the central atom. So 1, 2 electron sets are coming from bond, and then notice these 2 lone pair of electrons. So each lone pair counts as a set. So 1, 2, 3, 4. There are 4 sets of electrons, and whenever you have the 4 sets of electrons, the bond angle, the geometry is tetrahedral around the central atom, right? So the geometry is tetrahedral, but there are 4 electron sets, but 2 out of them is the lone pair. And what does the lone pair do? So the lone pair sits in this and in this way. So now you're left with only the bent molecular shape. So the molecule will have the bent shape, and the bond angle will be less than 109.5, which was in the tetrahedral, so it's somewhere around 103 degree. So the 2 electrons, what are they doing? They require basically more space, and that decreases this bond angle. So the geometry will be, or the molecular shape will be referred to as a bent shape. Now, depending on these shapes, you can predict whether a molecule is polar or non-polar. And for that, for a molecule to be polar, there has to be 2 conditions. One, it has to have polar bonds. And second, the bonds should be separated. So bonds must be arranged such that the separation of the charge exists. So let's look at what it means. So if you are given a methane molecule, which is CH4, and if you have to draw from the Honk rule, you know carbon forms 4 bonds. There are 4 hydrogens. This one is sitting in this, carbon is sitting in the center, 4 hydrogens are outside. Now let's count the number of electron sets on the central atom. So 1, 2, 3, 4. So there are 4 electron sets, 0 lone pair, right? So whenever we have 4 electron sets, what is the geometry? The geometry is the tetrahedral geometry, and that's what is shown here. And the bond angle is 109.5 degrees. And this is how the tetrahedral shape will look like. Now to determine if the bond is polar or not, what do we know about the carbon and hydrogen bond? Carbon is more electronegative, right? So this is delta positive, this is delta negative with respect to hydrogen. So here these arrows are telling you whether these bonds are polar or not. So the carbon hydrogen bonds are polar, but when they come together in this shape, what happens is they cancel each other out. So this one cancels to this one, and these two cancel. The polarities basically gets cancelled, and that's why this molecule becomes non-polar. So methane is non-polar. Next is ammonia. So you have NH3. Okay. So ammonia has nitrogen, and you know nitrogen form 3 bonds. So you draw the 3 bonds and the Lewis structure, and when you count the electron sets, you have 1, 2, 3 from the nitrogen. So if I have to draw nitrogen, hydrogen, excuse my drawing, and then the lone pair is sitting on top. So you have 3 bond pairs and 1 lone pair. So there are 4 electron sets, but it involves a lone pair. So what happens? So even though this is looking like a tetrahedron shape, remember there is 1 lone pair of electrons. So this lone pair electron is lone pair of electron. And then what happens to the geometry when you have a lone pair? In this case, it becomes a trigonal pyramidal molecule. So this is how the trigonal pyramidal molecule will look like. And for the polarity of bond, you know, between nitrogen and hydrogen, nitrogen is more electronegative, so that's why the arrow is pointing towards that. And these two polarities would cancel, but this polarity goes up in this direction, so that makes this molecule polar, because all the nitrogen hydrogen polar bonds do not cancel each other. In methane molecule, all carbon hydrogen polar bonds, they canceled each other, but in ammonia they do not cancel each other, and that's what makes this bond polar. And here's the molecular or a 3-dimensional view for you, electron density map as well. Okay, so the last molecule here is a water molecule. So water molecule, we all know H, O, H, and then it has lone pair, right? So it has 2 bond pairs and 2 lone pairs. So even though there are 4 electron sets, which would have said tetrahedral shape, right? But because you have these two lone pairs occupying the two sides, what is left is then hydrogen, oxygen, hydrogen, which makes for the bent molecular shape, right? So in this bent molecular shape, what happens is between the oxygen and hydrogen, you know, oxygen is more polar, so it's going in this shape. Now up towards oxygen, this is another polarity. And then they both, if they were in a linear, if it was a linear molecule, they would have cancelled each other. But now, because they are at a certain angle, they do not get cancelled, and which makes water polar. So water is one of the most polar solvent, and that's why, that is because of this bent geometry of water. So this is how you will practice and know. I will not ask you to draw all these things, but this is the logic behind how you know whether, depending on the shape, if something is polar or not. So know your table well and these steps, and you should be good. So how does this bonding help? And this is the last slide, which is basically showing you how chemical bonding and this molecular geometry and these different theories that exist, what do they do and how are they useful to us? So here in the picture you can see an example of vancomycin, which is a type of antibiotic, and what is it doing here is it forms a selective hydrogen bonds with these peptides of the bacteria, and it prevents the cell wall formation. So by using these molecular modeling, you can see how these bonds are formed, what pocket of the proteins will this antibiotic fit in, and how it will carry out this function. So we can design different molecules, develop new medicines, vaccines, depending upon these structural studies, and that can contribute to help in the health field, or in general, be beneficial for the development of medicines and have minimum impact on our environment and health. So this is one of the molecular modeling example that shows how these shapes are and geometries and these theories form the basis of this research. So in chemical vocabulary, when you talk about the name, you write it down like ammonia, right? In this case, ammonia, name is ammonia. When you refer to chemical formula, you actually represent ammonia in terms of its elements. So nitrogen, hydrogen, and there are 3 hydrogens in ammonia molecule. So NH3, it stands for ammonia, and that's a chemical formula of that. Then you go one step further and you have to draw the Lewis structure. You will show the 3 nitrogen-hydrogen bonds and then the lone pair of electron. And then from there, you can develop the molecular geometry of ammonia. So this is what we studied in this chapter.